class, this video is on topic D3, Magnetism and Magnetic Fields. So I just like to start out by saying that so far in this unit, we've talked about electricity and circuits, and you might not know the connection between electricity and magnetism until next lesson, lesson D4. So right now, some of the magnetism stuff might seem like you've learned it before, but note that a connection between electricity and magnetism that is totally brand new is coming up in the next video. So it's important to know, to really understand the fundamentals of magnets, just as much as it was really important for us to understand the fundamentals of circuits, which sort of look familiar from grade 9. So let's talk about magnets. Magnets have two poles, a north pole and a south pole. Similar magnetic poles repel, while opposite magnetic poles attract. This is called the law of magnetic poles. The magnetic poles always occur in pairs, and the poles are equally strong. So in this picture, we have what's called a horseshoe magnet with a north and a south end, or a bar magnet with a north and a south end. So the laws of magnetic poles include what we've already stated: like poles repel, while opposite magnetic poles attract. So you might have learned laws of electric charges, which is similar, saying that like charges repel, opposite charges attract. Maybe there's the law of romantic connection, and that opposites attract, and that two like people repel. So maybe this is very easy for you, but we're going to apply this in a number of ways this year, and also next year with the law of electric charges in next year's grade 12 course. So the second law of magnetic poles is that the magnetic field is strongest at the pole. This also should be intuitive. If you take a bar magnet and you want to pick up something, you're going to angle the object that you want to pick up, that maybe you're testing a paper clip, seeing if you could pick it up with a magnet. You're going to angle the bar magnet towards the paper clip with like aiming towards the pole. Because you know at the pole the magnetic field, and therefore the magnetic force as a result of the field is going to be strongest. The third law of magnetic poles is that the north and south pole in a bar magnet are usually the same strength. And the fourth one is if you cut a magnet in two, each half will possess a north pole and a south pole. So here we have a north pole and a south pole. If we cut it in half, you might think, will I just get a south piece and a north piece? But this end will still be south, and what used to be the middle of the magnet is now going to be the north end on this side and the south end on this side, and then this will be the north end of the other piece. And magnets can be natural if they're made from magnetite, Fe3O4. But also we have ferromagnetic materials that are not naturally magnetic but can become magnetized when placed in an external magnetic field. So let's further talk about different types of magnets. We have permanent magnets. So this is like your fridge magnet. It retains magnetic properties with or without an external magnetic field. And then there's a temporary magnet. So this is made out of ferromagnetic materials. So they perform like permanent magnets when in the presence of a magnetic field, but lose magnetism when not in a magnetic field. So if I take a bar magnet, that would be a permanent magnet, and I go to pick up a paper clip. Now the paper clip is not normally a magnet, but when you place it near a permanent magnet, the paper clip becomes a magnet. So it is a temporary magnet. It is a magnet when in the presence of a magnetic field. You can test that out by taking the edge of a paper clip close to a magnet. Then the opposite end of the paper clip can be used to pick up another paper clip. So just like you're playing Barrel of Monkeys, you can have a long string of paper clips, and they are held together by attractive magnetic force. We also have, very important in this chapter, is electromagnets. So these are magnets that you can maybe see from the name, we use electricity to turn on and off the magnet. So that's why we call them electromagnets. It is made up of a coil of wire that will function as a magnet when electric current is passing through it. And so this hopefully this is kind of like a magical statement for you right now, because we've never talked about current causing a magnet to be created. And we're going to take a couple of topics, the next couple of topics, to talk about that. This is how a subwoofer works. So if you think of a speaker that produces bass notes, if you actually look at it, there's this giant circle that is coming out at you and then going back into the speaker repeatedly at a fast rate. And the reason why it goes in and out is because there is repulsion of a magnet from the base of the cone to the base of the speaker. And then there's repulsion. So the cone pushes out, and then there's attraction and the cone pushes in. So a subwoofer is an example of an electromagnet. And the advantage of electromagnets, we can turn them on and off. The strength of the magnet can be altered. And there's a lot more to say about electromagnets. So a magnet produces a magnetic field in the space surrounding it, in which causes a magnetic force on a second magnetic object. So a compass is an example of a magnet. It's just a very small magnet that is pivoting or floating. If we took a magnet, a bar magnet, and tied it with a string and then held that string, that bar magnet would be free to float around, and that bar magnet would act like a compass. The north pole of a magnet always points to Earth's geographic North Pole. So that's where Santa lives. So that's what a compass is. A compass is a bar magnet that is free to spin around. We also have a horseshoe magnet. So anything that has magnetic properties would feel a magnetic force if placed in a magnetic field. We've talked about a field before, the gravitational field. So when you place something with mass in the gravitational field, there's an attractive force. So when we place a magnet in a magnetic field, there is an attractive or repulsive force. So let's say this is our bar magnet. And if we were to place a whole bunch of compass needles around this magnet, all of those compass needles would orient towards the south pole of the magnet and away from the north pole of the magnet. I should mention that the compass needle, there's like 2 points on the compass needle, but we look at the red side. The red side of the compass needle is a north magnet. Remember that opposites attract. So the north side of this mini bar magnet is attracted to the south side of this big permanent magnet. And then similarly here, the north side of this mini magnet is repelled and it will point away from this north magnet. The space surrounding a magnet is the magnetic field, and that's the space where a magnetic force can be detected. This force is a force at a distance. So recall in the forces unit, we had like forces like applied force, friction, tension, normal force, gravity. Those all required contact. And there was only one force that we learned, the force of gravity, that was a non-contact force or a force at a distance. Now here is a second force, because gravity is not the only force. Magnetism is a force at a distance. So this bar magnet does not actually have to be touching that one for feeling the effect of the force, the attractive force. A compass needle is a magnetized piece of metal, needle mounted in such a way that it can spin freely. And if we were to put compasses all around a permanent magnet, we would find these field lines. And if we put enough compass needles and connected all those line segments, we would see these magnetic field lines. A compass can be used to map the direction of field lines around a magnet. The compass needle will align itself along the direction of the field. So what are field lines? Field lines tell you the direction that a north magnet would point. And also the density of the field lines tells you the strength of the force. So if you take a look at where are the lines most dense in this diagram for a bar graph, that is in line with the laws of magnetic poles, that the force of the magnetic force will be more strong at the poles. So you can see here the line density is higher, and therefore the force of repulsion for a north magnet here would be the strongest. The force of attraction would be the strongest here near the South Pole. And we also have an example of the magnetic field lines around a horseshoe magnet, which still go north to south, still are more concentrated at north. And also the Earth is it's sort of just a giant bar magnet. Now notice here, the red north magnetic needle will point to the South Pole. Hi class, sorry about that brief interruption. That was my cat getting her food again from her automatic feeder. Okay, so we were talking about Earth having a North Pole and a South Pole. If we put compass needles all around the Earth, that north compass needle points up here where Santa lives. But if you recall, opposites attract. The red north needle of a magnet is always pointing to the south magnet, south pole of the original magnet creating that field. So from this, we conclude that the North Pole, the geographic North Pole of Earth, where Santa lives, is actually a south pole of this bar magnet, and the North Pole is down here. We'll talk about that more in a moment. But what did we notice from all three of these diagrams? We noticed that the magnetic field lines, after putting several compass needles all around the magnet, we noticed that outside the magnet, these magnetic field lines always point north to south. So it's technically true that inside the magnet, the direction is south to north. So there's a closed loop north to south. And then if we could see inside this magnet, it would form a complete loop south to north. But the one that we're really concerned with in grade 11 is the fact that outside the bar magnet, or outside any magnet, the field lines go north to south. Notice that they are closer together at the poles. That's where the force is the strongest. So attractive force here for a north magnet, and repulsive force here for a north magnet. Notice, we haven't talked about this, they never cross. So the field line direction is telling you where the compass needle will point if you place a compass there. And I like to think of like the reason why they can never cross is there has to be one answer for the direction of the force. One answer. If you had lines crossing, then the compass needle would be confused which direction to point. So you can never have magnetic field lines, or any field lines for that matter, crossing. These, at least these are properties of other field lines. So in grade 12, we talked about gravitational field lines in more detail, and we also talk about electric field lines. So there's some things you learn from this that are fundamentals for our foundations for next year. Okay, in this simulation, I'm going to put a link below to this simulation. If we take two bar magnets, put them on a desk, and we sprinkle iron filings all over the desk, so just tiny pieces of iron. Because iron is ferromagnetic, if we allow the pieces of iron to move, then they will orient themselves along the field lines. So far in this lesson, we've talked about magnetic field lines being visible if you have a compass or several compasses around the magnet. And the other way is if you sprinkled iron filings. Like this. This is what iron filings look like. And notice that not only you could notice some of the properties of magnetic field lines that we talked about, like that they're more dense at the poles. So you can see the field lines coming out of like right at the pole are more dense. So the force is strongest there, and then they kind of radiate outwards. So you can see that. You can also observe one thing here that we didn't talk about in that list, which is that the field lines are three-dimensional. Some ones over here, these spikes are pointing out this way, and on the other side, they're pointing back. So they're three-dimensional. We can use magnetic field lines to predict the direction of magnetic forces. So if you put a south magnet facing a north magnet, near the north magnet, the magnetic field lines will point up and away. South magnet, they will point towards. And if you look right here, a compass needle would point down, and right here, a compass needle would point up. So it turns out when opposite magnetic field lines are near each other, nature wants to bring them closer together, and that's another way to remember that opposite magnetic poles attract. If we look over here, we've got the magnetic field lines pointing towards south here and towards south here. Those two, if we put two compass needles here and here, those two neighboring compass needles would go the same direction. And when magnetic field lines go the same direction, there is repulsion. And we also could just look at the poles, south and south, opposites attract. You might wonder if the rule is so easy, like opposites attract, could you just look at the poles? We are going to be doing problems later in this unit where you don't necessarily know that it's a south pole or it's not as clear as this. So it does help to know the direction of the field lines compared to their neighbor. Does give information about the force, the magnetic force as well. Okay, we were talking about that Earth is a giant magnet, and actually the south magnet is at the geographic North Pole where Santa lives, and the North magnetic pole is at the geographic South Pole where the penguins live. So Earth has its own magnetic field inside and surrounding the Earth, which is offset slightly from the geographic poles. And some applications of this are like navigation. So we can use a simple compass to find the North Pole. Animals use the magnetic field lines to navigate. There's also the Aurora Borealis, which is also known as the Northern Lights. So it turns out that the sun, we tend to think of the space between the sun and the Earth as empty, but there is charged particles. So this, we could think, I think I've heard the phrase cosmic rays from the sun. And there are charged particles that exist that are sent from the sun to the Earth. As those charged particles are coming closer to the Earth, they are affected by the magnetic field lines, and they actually start spiraling like a corkscrew up these lines. And that's why you see it more in the north, and you call them the Northern Lights. There's a lot more details about that. And again, that's more of an application that you learn in detail in grade 12, but even in grade 11, you can learn that the Northern Lights is an application of Earth's magnetic field. Here are some examples of animals that use the magnetic field lines to navigate. So lobsters, birds, fish, turtles. There's also technology that uses magnets. Maglev trains, particle accelerators, and magnetic resonance imaging. So these are 3 applications that have a little blurb in your assigned reading for today. And for this, associated with this video, you don't have to do it today. And it would be good if you could come up with just like a quick 1 or 2 sentences about why each of these use magnets. So I will leave that up to you. So your practice questions, you only have 2 practice questions, but I really will recommend that you read the textbook, which is page 548 to 552, especially to read about each of these technologies and write a little blurb about each one of them, because you may be assessed on the technologies that use magnets or the applications of Earth's magnetic fields. So it's only 2 questions, but there are several parts to the questions for page 552, 5, and 6. So I just want to take a look at it and give you some tips, because you're going to be doing some drawings. And there's not full solutions of the drawings in the solution manual. So number 5 says, copy the diagrams in figure 8 into your notebook and show the directions that the compass needle would point. So if this is a bar magnet, I'm always going to start drawing magnetic field lines that go away from north and come back to south. So if I was a compass needle over here, I would be pointing away from north, so that would be to the left. So when you're given a question where the compass needle or the compass face is blank like this, there's no needle, what you're asked to do is fill in the direction of that little mini bar magnet that is your compass needle. So this would be to the right. And we know that the north side of the compass needle points away from north and towards south. So this would also be to, away from north. So this would be to the left. Then over here, it would be to the left, but it would be towards south. And if you connect that line with that line, you actually get this loop, and you'll see over here the compass needle would point to the right. So here it's to the left, to the right, to the left, and over here you have a closed loop from here to there. So that's how you would do those, and you have part B to still do. For question 6, there's no compass needle, although it sometimes does help to imagine there's a compass needle there. You have to draw the magnetic field lines for each of these. And if I were to assess this, I would be looking for 3 things. So I'm not looking for creativity or artistic, I guess, neatness. What I'm looking for is the 3 properties of magnetic field lines from this lesson. 1, the direction of the lines is north to south. So for example, here you're going to start with north to south, a loop on this magnet. Then you're going to do a north to south loop on this magnet. Then maybe you'll have some lines that go from this north to that south. The next one is that the lines are higher density at the poles. So when you've drawn one loop here, you're going to draw your next loop that is very close to that first loop when it originates from the North Pole, but then it's going to spread out, maybe go over here and then coming back in the South Pole. And then the third thing is that the field lines can never cross. If you have a bar magnet on its own, it's so much easier to realize that they don't cross or to not make that mistake. But notice part A, you've got 2 bar magnets. And then for part B, you have 2 bar magnets. You have, for part C, a bar magnet and a horseshoe magnet. So just be careful that your field lines don't cross. And that's it for this video. Please practice those questions, submit them, and complete the exit ticket for this video. Have a great day.